recording this one. So today we're talking about thermochemistry. Thermochemistry. All right, so we're continuing what we talked about with the calorimetry stuff, because calorimetry we're studying heat, thermochemistry we're studying heat too. Okay? When we talk about thermodynamics, we're technically talking about heat and its conversions. Okay? So when you hear the thermo prefix, you're specifically referring to heat. That's all that means. Okay? Calorimetry, we were looking at heat too. Okay, so calorimetry falls into this family. Now this is a preview of things to come, because next semester in Chem 2, for those of you taking Chem 2, which I hope everyone in here is taking Chem 2, we're going to spend more time going into thermodynamics at an even deeper level. So right after spring break actually is when we start thermodynamics. So thermodynamics tells us a whole lot of really useful information, like will a reaction happen? Yes or no? That's a really good question to ask, right? Thermodynamics answers that question. So we'll spend a lot of time next semester talking about thermodynamics. Here we're just kind of peeling back the first layer of that onion. All right, so let's pick your favorite sports team. Got a lot of athletes in the room, so think about yourself. Now I guess if you're an athlete, your rules are a little different than if you're a spectator ion like me. But let's just pretend you're picking your favorite professional sports team, right? Someone you're a spectator of. Do you care how your team wins? I know I don't. My husband might care because he's a lot more obsessive about that stuff than I am, but I don't care, right? If I'm watching my favorite team play, I just care if they win, right? Woo, you win. There are a lot of ways you can win. You could beat them bad. You could beat them by a tiny margin. You could be up the whole time, come from behind. Right now, I say most folks only care that they win. Now, if you're a player, if you're the coach, I guess that's a little different. But if you're watching some professional sports team, of which you are not a participant, you are a spectator, most people are just happy that they win, right? And so heat is analogous to that, okay? In heat, when we're studying heat, we're not looking at the path, okay? We're not interested in the path, because heat is called a state function. State function. So in a state function, this means that we're not interested in how we got there. We're just interested that we're here, just like you right now. I don't really care how you get here, right? You could ride a bike, you could take a bus, you could walk, you could drive your car, you could fly an airplane, you could go on a boat, right? Getting here by boat would be kind of tough, but you know what I mean, right? The fact that you're here is all that I care about. The fact that you're here, I don't care how you get here, just that you're here, right? State function is analogous to that in the sense that we don't care how we get from point A to point B. We're just looking at the end result, right? So for instance, if I take water at 0 degrees Celsius and heat it up to 50, would that in any way be discernible from water that was taken from 100 degrees Celsius and cooled down? Could you tell any difference in that? No, you wouldn't, right? If you are blindfolded and there are 2 beakers and you stick your finger in each one, 50 degrees Celsius, that'd be pretty hot, but nonetheless, you stick your finger in each one, right? You wouldn't be able to tell, oh, this one definitely came from the ice and this one definitely came from the cool water. No way of knowing that, right? Now this is different from kinetics. Next semester in Chem 2, we'll study kinetics as well, and kinetics does care about the pathway. Kinetics cares about the pathway tremendously, but thermodynamics doesn't care about the pathway. We just look at the initial and final. We don't care what happens in the middle. Right, so there's a pictorial representation of that, right? Cooling versus heating, the end result, you wouldn't be able to discern. Okay, that's a state function. And so enthalpy is another word for heat, right? We represented enthalpy this week when we did calorimetry with lowercase q. We also represented enthalpy with delta H, okay? Q and delta H mean the same thing. Remember when we were doing the heating curves, we talked about delta H of fusion, delta H of vaporization, right? We said Q is equal to number of moles times delta heat or delta H of fusion. That's the same thing we're dealing with. Okay, delta H and lowercase q are the same thing. So the amount of heat associated with a particular reaction is called the enthalpy of reaction or the heat of reaction, right? Does your reaction produce heat or does your reaction consume heat? If you've ever stood next to a fire, you've experienced a reaction that produces heat, right? So if you have some sort of flammable gas, you take your candle to it, provide the activation energy, it explodes, right? That's producing heat, yes. So if you've ever been around a hot packs, right? You break those little packets and they make your hands feel hot. There are also cold packs, work the same way, right? Those absorb heat. Okay, so the heat of the reaction is associated with how much heat is generated or consumed by your chemical reaction. All right, so the overall change, delta always means change in, and it's always final minus initial, right? So if we're talking about a chemical reaction, what is the final state? That's the products. What's the initial state? That's the reactants, right? So delta H, in other words, the change in enthalpy for my particular reaction is the enthalpy associated with the products, because that's the final state, minus the enthalpy associated with the reactants. That's the initial state, right? Anytime you see delta, uppercase delta, right? Lowercase delta looks like an 8 that you didn't fully close. Uppercase delta looks like a triangle. So anytime you see uppercase delta, whether it's delta T or delta S or delta G or whatever, right? Change in is always final minus initial. Products are your final, initial is your reactants, okay? Now we interpret delta H the exact same way that we interpret Q, okay? We interpret delta H, we interpret Q identically, because delta H and Q are the same thing, okay? Lowercase q, right? Not uppercase Q. Uppercase Q is reaction quotient, which we'll deal with when we talk about equilibrium next semester. If delta H is positive, this is endothermic, right? Because the products are hotter than the reactants. How do you get a positive delta H, right? Final minus initial. So if we get a positive delta H, that means it's endothermic. If we get a negative delta H, that means it is exothermic. Okay, so endothermic means what? Is heat being absorbed or released? Endo sounds like what? Absorbed. Sounds like enter, right? Just like endocytosis, if you're thinking about biology. And if delta H is negative, exothermic, is heat being absorbed or released? Released, right? Right, so here's endothermic, if you want to picture it, right? Heat going in, and there's exothermic, heat going out, okay? So just by looking at these delta H values for these reactions, tell me, are they exothermic or endothermic? What's the first one? Endothermic, right? Positive delta H. What about the second one? Exothermic and endothermic, right? Is everybody cool on how to interpret this? Just look at the sign of delta H. Delta H is the same thing as Q. Now there are two ways we're going to calculate delta H for a reaction. The first one is called Hess's Law. That's what we're doing today. And the second one is standard enthalpies of formation, which we'll do on Monday. By the way, you might want to bring your textbook with you on Monday. I know we don't always refer to it during class time, but there are some appendices at the back of your textbook that we'll be using. So if you have your textbook, you might want to make a note to yourself to bring it on Monday. But we're only doing Hess's Law today. And so how do you pick the one to use? It's based on what you're given. Okay, so let's talk about Hess's Law. Hess's Law says that if we add up all the steps that make up a reaction, if we know the delta H of step 1 and step 2 and step 3 and step 4, we can add them up and get the overall reaction, okay? Because many reactions don't occur all at once, right? The process that occur in our cells, for instance, are a great example of that. Think back to biology. Think about all those steps you have in cellular respiration, right? That's a long process. That's multiple steps. If you take delta H for step 1 and step 2 and step 3 and step 4, right? Add them all up. That's how we get delta H for the overall reaction. So let's look at this reaction. A plus B plus C producing ABC. Now it doesn't occur all at once, it occurs in 2 steps. Now I want to know delta H for this reaction. So if there's step 1, and it's delta H, and there's step 2, and it's delta H. Now here's the key to Hess's Law. Okay, when you're doing Hess's Law problems, you're going to be given reactions that contain substances that you may not want in your final reaction of interest. So notice, is AB something that we want in my final reaction? Is my final reaction the one I'm interested in containing AB at all? Yes. AB? No, it contains ABC, but it doesn't contain AB, right? So I need to find a way to manipulate these so that the ABs will cancel out, right? But notice, if I just add them up right now, what would happen to the ABs? They cancel, right? Because the same exact one is on the products as is on the reactants, right? So here it just happened to work out because I made it that way, right? That they're the same ones on the products and on the reactants. They have the same coefficients, so I can cancel them out. But in Hess's Law, a lot of times you'll have products where maybe you got to reverse one of the reactions to get something you don't want to cancel out. Maybe you got to multiply everybody by 3 to get something to have the right coefficients, okay? So if you like working puzzles, this is definitely something you'll enjoy. This is kind of like using that other side of your brain. But anyway, all I have to do here is add them up. So delta H for the reaction is just 4 plus 8, so 12 kilojoules. Okay, does this make sense? Now, obviously, the ones you'll be dealing with are a lot more complicated than this. But if you understand the basic principle, you can apply it to any situation. So, again, we work backwards from the reaction that we want. We work backwards from whatever our desired reaction is. Sometimes we may have to reverse a reaction, but let me ask you this. If you reverse a reaction, the products are now reactants, and the reactants are now products. So what do you think that does to the sign of delta H? If delta H is products minus reactants, and you've now reversed the products and reactants, what do you think that'll do to delta H? It will reverse it as well, right? So if you reverse a reaction, make sure you reverse delta H's sign. Don't take the inverse of it. That's totally different. Just change the sign. Okay? If you multiply everybody by 3, great. That's awesome. What do you think you need to do to delta H? What would you do to delta H if you multiplied everybody by 3? You would multiply delta H by 3 as well, right? Or if you divide everybody by 2, okay, make sure you do the same thing to delta H. Whatever you do to your reaction, you do to delta H as well, okay? And so as you're doing these kinds of problems, if you just kind of write a little note off to the side, times 3, or divided by 2, or times 7, or reverse, all right? If you just jot 1 or 2 words telling me what you did, that way I can make sure that you did it to delta H correctly, okay? Because maybe you reversed it, but you forgot to change the sign of delta H. I could still give you partial credit if I know what you were intending to do. Okay, so always just give me 1 or 2 words telling me what you're doing. So let's just practice manipulating reactions. Before we get to calculations with Hess's law, let's just practice manipulation. So if the reaction A plus B forms AB has delta H of 290, what would delta H for the reverse reaction be? If I reverse that, what would that do to delta H? I've seen students take the inverse before. Is that what you do? Is delta H 1 over 290? No, it's the, just change the sign, right? If going this direction has positive 290, that means going this direction would be negative 290. Okay, so if you flip the reaction, just flip the sign of delta H. Okay, here's the original reaction. Now I've got this reaction. What did I do to get from this to this? I multiplied by 2, right? So what would I need to do to get my new delta H? Multiply it by 2 as well. Okay, so whatever you do to the reaction, do to delta H. So if you reverse it, reverse the sign. If you multiply by 2, multiply by 2. If you divide by 2, divide by 2. Okay, anything you do to your reaction, make sure you also do to delta H. Does this make sense? Okay, so now that we're good at this, here's one for you to try. Here's the reaction you're given, and it's delta H. I want to know delta H for this reaction. So figure out what happened between here and here, and then make the corresponding changes to delta H. All right, let's see if you got it right. So what did we do to get from here to here? We did 2 things. What were they? Reverse and multiply by 8. Right. So you're going to do the same thing to delta H, right? So multiply by 8 and reverse. 3 sig figs, 3 sig figs. So negative 1,990. Do we agree? Anything you do to the reaction, you do to delta H. Okay, so like I said, the goal of Hess's law is to get anything that you don't want to cancel out and to keep all the things that we do want. And then we'll have to also make our coefficients match those of the desired reaction. So that means dividing by, multiplying, etc. So let's do this one together. Carbon's got 3 allotropes, right? It's got carbon graphite, carbon diamond, carbon buckyball. And so let's pretend we've got graphite. That's what's in your pencil right now. And you want to turn it into diamonds. You want some extra cash. All right. So if I'm going to turn my graphite into a diamond, what's delta H for that reaction? Here are 2 reactions for the combustion, for a reaction with oxygen to produce carbon dioxide. So there's graphite plus O2 is delta H. There's diamond plus oxygen to produce CO2, this delta H. What do I need to do to these two reactions so that I can figure out delta H for this reaction? It's an easy solution. What is it? You can figure it out. Do we want diamond to be a reactant or a product? A product, right? Because I'm turning my graphite from my pencil into diamond. So that means diamond needs to be a product, right? So which one of these reactions do I need to reverse? The bottom one, right? Because if I want diamond to be a product, I need to reverse the bottom reaction. And then, conveniently enough, if I reverse the bottom reaction, the CO2s cancel, the O2s cancel, which leaves me with graphite to diamond. Hey, it only takes 2 kilojoules. Great. I can go put my graphite in the microwave this weekend and I'll have diamonds. But try it out, see what happens. Actually, don't put graphite in the microwave. Maybe you just heat it in a hot bath, see what happens. The answer is you're not going to get diamond. Spoiler alert. Well, this is only one piece of the puzzle, right? When we get into Chem 2 next semester, we'll talk about Gibbs free energy and change in entropy, which also factor into whether or not a reaction happens. Right? This is just looking at the energy component. It's not going to factor in, is this reaction going to occur? And it's not also factoring in how long it's going to take or any of that good stuff. So we're just literally scratching the surface of thermodynamics right now. But does everyone understand how we use Hess's law here? Yes? All right, you do this one. Here's the reaction I'm interested in. I want to know its delta H. This is what I'm given. So take a minute, figure out what you need to do to these two reactions so that they add up and give me this, and then add up your delta H's and get the delta H for the reaction of interest. All right, so we have to look at what we're given and find a way to manipulate it so that it matches what we want, right? So for instance, I'm going to want the coefficient of sulfur to be 2. I'm going to want the coefficient of oxygen to be 3. Right? So I need to find out some things to do. There's only one thing you have to do in this reaction. What is it? What do you do? This one's pretty easy. All right, all you do is multiply it by 2. All right. And then when you add up, all the SO2s go away. They cancel. Gives you the desired reaction. That's all you had to do. So if you just off to the side wrote multiply number 1 by 2, that's all you need to do. You don't have to rewrite it like I did. Now, if you want to rewrite it, that's great. You don't have to, though. If you just, or if you put parentheses around the whole thing and wrote times 2, that's fine, too. Okay, just show me what you did in some way so that if your delta H comes out funky, I can at least see what you were trying to do, give you partial credit. All right, try again. Here are 2 subreactions, and their delta H's, and I want to know delta H for this reaction. So take a second, figure out what you need to do. See if you get this one. All right, so let's look at what we have versus what we want. We're obviously going to need to do some multiplying, right? We're obviously going to need to do some reversing because NH3 here is a reactant and we want it to be a product, for instance, right? So we're going to need to do some reversing. We're going to need to do some multiplying. So here's what I did. I'm going to show you every single step one at a time. Now, again, you don't have to rewrite it every time. If you just write a couple notes, a couple bullet points telling me what you did, that's fine. So the first thing I did is that I reversed reaction 1, just so that everything's in the proper place, right? I want N2 to be a reactant, so I reversed it. And then I multiplied it by 4, because I want my coefficient to be 2, right? 1/2 times 2, 1/2 times 4 gives me 2. So I multiplied that whole reaction by 4, which means I also had to do it for delta H as well. Then I had to reverse reaction 2, right? Because I want H2O to be a reactant. And then I multiplied it by 3 to get my H2s to go away. So then when I add those things up, I get the desired reaction and a delta H of 1268. For following sig fig rules, we should round that up to 1300. But if you left it as 1268, I probably wouldn't count you wrong. If you want to be technical with your sig figs, that would be 1,300. Now, if you did yours differently, but you got the same answer, that's fine. I've had students before, they'll wait till the very end and reverse the entire reaction. That works the same, right? Because if you add it up, you get the entire thing just backwards, and so then you just say, okay, flip it. That works too. Okay. Or maybe you multiply by different factors, but you still get the same final answer. How are we feeling about this? Feeling pretty good? Feeling pretty good? It's not too bad, is it? I don't think it's too bad. I think it's kind of fun. Okay, let's look at this one. Studying ways to convert nitrogen monoxide and carbon monoxide into less harmful gases. And here's the reaction we're interested in. Here are the two reactions we're given. So what is delta H for this reaction? Pause the recording. Okay, so we have to do some manipulations here. Here's what I did. If you did something different but you got the same answer, that's possible. So the first thing I did is I took equation 2 and I multiplied it by 1/2. In other words, I divided by 2. That's what I did. And then I reversed it, and then I added. I left reaction number 1 alone. Did you get the same thing? Everybody figuring out how to do this? Okay, try this one. Prove that delta H for this reaction is negative 18 kilojoules, given these 3 reactions. I want you to demonstrate that delta H is negative 18. Okay, so the solution to this is a lot easier than it implies, right? You just have to reverse one of the reactions and all the dominoes fall down after that, right? If you reverse the last one, everything you don't want to go away, everything you don't want in your final reaction goes away, right? Bye-bye, 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 bye-bye. And that's it. So sometimes you see a whole bunch of steps and you're like, oh, but just take a deep breath, look at it and go, oh, okay, you know, this really isn't that bad. Don't be overwhelmed by the number of substances listed. All right, here's the last one for today. Delta H for this reaction. Anytime you see this little degree sign, that just means under standard conditions, okay? It has nothing to do with temperature. This little degree sign means under standard conditions, so don't panic if you see a little degree sign. All right, last one. Let's go over this one. So I took number 1 reaction and multiplied by 2. I left equation number 2 alone, and then I reversed equation 3 and divided by 2, otherwise known as multiplying by 1/2. That's what I did. And so that made the things that I don't want go away and left me with a value of 226.6 kilojoules. Any questions on this one? We all Hess's Law experts now? All right. Well, that's where we'll stop for today. Have a good weekend, and I will see you on Monday.